Alright, so in this video we're going to cover questions 3 and 7 from the second review packet. So an ant moves along the x-axis from left to right at 5 inches per second. So we've got an x-axis here. A spider moves along the y-axis from up to down at 3 inches per second. At a certain instant, the ant is 4 inches to the right of the origin. Alright, so I'm just going to draw a little picture here. The ant is 4 inches, so I'll say x equals 4 at a certain time. And the spider is 8 inches above the origin, so we'll say that's y equals 8, and that's the spider. At this instant, what is the rate of change of the distance between the spider and the ant? So what I want is the rate of change of that side z, we could call it. All right, so I could find the exact value of z at this time when the ant is 4 inches to the right and the spider is 8 inches above. There is other information that we have here though, so let's just catalog some of the details that we've been given. Okay, so first of all, x is going to equal the distance that the ant is from the origin, and y is the same but for the spider. So then if that's the case, then z is the distance between the ant and the spider. So let's consider the other things that we've been given. We've been given a rate for the ant and a rate for the spider. So in terms of these variables that we've identified here, the rate of change of the ant's position is going to be dx dt, and the rate of change of the spider's position would be dy dt. So then what that means for z is that dz dt is going to be the rate of change of the distance between the ant and the spider. And this is the thing we are trying to find. So our goal is to get an equation that identifies dz dt, where everything else will be given or have a value for it. So what we want to think of is an equation that might connect the three sides of a triangle, and in this case this would be a right triangle. And of course our choice then is going to be the Pythagorean theorem. So in the Pythagorean theorem we have a squared plus b squared equals c squared, which in our case is actually x squared plus y squared equals z squared. Now this is not going to help us a whole lot to find the value of dz dt right now, but it is going to help us find the value of z right now, which is a value we're going to need to know. So let's go ahead and find that. So in this case, x is 4, y is 8, and z is unknown. Okay, so in this case, 4 squared plus 8 squared is going to be 80. And so then z is equal to the square root of 80. And there is a perfect square that I could pull out of 80. That would be 16. So the square root of 16 is 4. That leaves us with a 5. So I'm going to call z 4 radical 5, and now I can go back into my picture here and call this 4 radical 5. Good. So that's important information that we need to know. Now let's go back to the Pythagorean theorem and use this to give us the value for dz dt. Since I'm trying to find dz dt, I am treating each of these like functions. Okay, so I'm going to differentiate implicitly here. And so I will have 2x times dx dt plus 2y times dy dt equals 2z dz dt. And a lot of these values I know. I know that x at one time is equal to 4, and at that time the rate of change is 5 inches per second away from the x-axis. So dx dt is 5 plus 2. At that same time, the spider is 8 inches from the origin, but it's traveling toward the x-axis. So dy dt based on the speed we were given, which is 3 inches per second, is -3. Now the reason that that's -3 is because if we go back to our picture here, the spider is headed this direction, the ant is headed that direction. So one of these animals is going towards the origin, the other one of these animals is going away from the origin. So if I were to refer to dx dt, I would want to indicate that that is growing, that it's moving further and further away from the origin. So that's why we say that that's a +5 inches per second. But with the spider, it's getting closer to the origin, and this value here is decreasing. So the 8 is shrinking slowly and becoming a number closer to 0, while the x is growing and becoming a number greater than 0. So with the spider, dy dt, I'm going to refer to that as -3 inches per second. And then we have 2 times z, which we've determined to be 4 radical 5, times dz dt. And this is good news because now we have an equation that contains the thing we want, and everything else has an actual value for it. So now we just have to work on solving. Okay, so 40 minus 48 is -8. And so when I divide both sides by 8 radical 5, I'm going to get -1 over radical 5 is equal to dz dt. Which, if I were to turn that into an actual numerical value, that is going to be approximately -0.45 inches per second. Which means that at this moment, the distance between the ant and the spider is decreasing by 0.45 inches per second. So let's talk about implicit differentiation with example 3. So we're asked to find dy dx, this is the thing we want, at the point 0, 1 based on this curve that we've been given here. So the first thing that I want to think about is how much work would it be to get y alone? Because if I could do that, that would be very easy. That would be incredibly challenging in this case, so I'm not going to do that. What I am going to do is differentiate both sides of this equation with respect to x, meaning x is a variable and y is going to be treated like a function. So when I differentiate the left side of the equation, dx of e to the xy power, and I differentiate the right side of the equation, I have to keep in mind that x is a variable. So the left side of the equation, when I take the derivative of e to the any power, that's just itself, right? So I have e to the xy. But there's a chain rule here because there's a function in that exponent of e. So I have to multiply that by the derivative of this function. There's a product rule happening here where my f function is x and my y function is y. So I'm going to have f times g prime, and the derivative of y with respect to x just has to be called dy dx because I don't know what that derivative would be, plus now I have to do g times f prime, y times, and the derivative of x is 1. Remember, x is a variable, y is a function. So then on the right side, it's very easy to take the derivative of x squared with respect to x, that's just 2x. But the derivative of y squared with respect to x is 2y times the derivative of y with respect to x. So now we should probably highlight the thing we're trying to find. We are trying to find the value of this. So our goal now is to get those two things to be together so that we can isolate them and get dy dx alone. So what I'm going to do is distribute this e to the xy. And now that I've done that, I'm going to make an effort to get this component and this component on the same side. So I'll choose this side over here, which means I'm going to have to send that component to the other side. So I now have x times e to the xy dy dx minus 2y dy dx equals 2x minus y e to the xy. And the reason I'm doing that is now I can factor out that dy dx from these two terms, leaving me with x e to the xy minus 2y. So now I'm just one step away from finally isolating that thing that I've been trying to find. Right here. I'm just going to divide by x e to the xy minus 2y on both sides. And there is a part b. So I found that dy dx is equal to 2x minus y e to the xy divided by x e to the xy minus 2y. So remember, the original equation wants me to know the value of this at the specific point, 0, 1. So now all I have to do is use this function that I have that allows me to tell the rate of change of y with respect to x and plug in those values. So I have 2 times x coordinate is 0 minus y coordinate is 1 times e to the 1, 0 times 1, try to be consistent there, over 0 times e to the 0 times 1 minus 2 times 1. And this comes together pretty easily here. You're going to end up with negative 1 over negative 2, or 1/2. So that is dy dx at this point. Or in other words, that's the slope of any tangent line that exists at that point on the curve that we were given. So part B asks for the equation of the tangent line at the point 0, negative 1. So they're changing the point up on us, and now we want a whole equation. So one thing I know about this final equation is that it's going to say y minus negative 1 equals something, that's going to be our slope, times x minus 0. And obviously there's a better way that we can write this, but this is just me using point slope form. Y minus the y coordinate equals the slope times x minus the x coordinate. So all I need to find now is the slope. And the nice thing is I have a function that gives me the slope at any point on the function. So all I need to do is, instead of plugging in the point 0, 1, I'm going to plug in the point 0, negative 1 here. So here I've plugged in my values. All right, so this is 0. This will be plus, and e to the 0 power again will be 1, divided by, I have a 0 plus 2. So 1/2 is that slope. So my final answer then is y, and I'm going to use keep change here. So y plus 1 equals 1/2 times x minus 0. And another way that we could write this, if I wanted to move it to slope-intercept form, I could call this 1/2 x minus 1.